So, how do you differentiate a probability model versus a sample data set? This is often one of the issues I encounter with students is you come to learn very quickly how to compute an average or a mean of a data set. So that's just a list of observations. It could be a list of participants' ages or the number of rings in a tree. And you've got many trees that you're gathering the data for. And getting an average is just adding them up and dividing by the number of values that you add together. And so students tend to pick that up pretty fast. But a probability model may look like data, but it isn't. It's a different format. In particular, the format that you will have to know that you have a probability model is instead of a list of observations, what you have is a table that tells you everything that could be observed and the likelihood or probability of each of those observations being seen. And so that's what I summarize at the top here, that a probability model is a table that says everything that could happen and how often or how likely they can happen. And so if you have all possibilities accounted for, then the sum of those possibilities must be 1 or 100%. So it's a nice quick check to make sure that you have a probability model and that it's complete. And once you do, then you could find things such as the mean and variance of that probability model. And the formula is a little different than what you've seen so far. So in this topic, you're going to learn how to differentiate between a collection of data and a probability model, which is what I just described. You'll learn how to compute the mean and variance of a probability model, which is computing it for a random variable. And you'll be able to answer questions that utilize those concepts. All right, so to find a mean and variance, you are going to be finding what's called an expected value. So the expected value of x is the mean of the random variable x. It is given by this first formula here. You'll notice that your symbol for mean is different than what you had seen so far. You've seen x bar, but this symbol is mu. It's the Greek letter mu. And mu is given by each of your observations multiplied by the corresponding probability, and you add up those products in order to get your mean. Now, for the special case where each observation is equally likely, meaning that the probability of each observation occurring is 1 over n, if you have n possibilities, that is going to simplify to just what you know is the average. And so that's why mean is a more general term. Average is a very specific type of mean. All right, so let me just talk about notation a little bit here, because you've seen a number of symbols up to this point. You should have seen n, little n for sample size. You've seen x bar and s squared. Now you've seen mu. And if you happen to have looked ahead, you would have even seen this circle with a line on top that is sigma, and this one is squared. And so why do all these symbols exist? Well, they exist because there's two fundamental concepts that you're going to need to really come to know and understand. And that is the difference between a sample and a population. Population is the entire group of interest that you want to study. And the sample is just a part of them. And so you may be interested in something about students at the university that you are attending. And there may be 15,000 of them, but you may only look at 100 of them. That 100 students is your sample, and the 15,000 that you chose them from would be your population. And so you have a symbol or a different symbol for each group. So the mean of the sample is this x with a bar, whereas if that mean came from the population, it would be mu. And so you have two means, and it's important to know, is it the population mean or the sample mean? Likewise, you have two variances. You've got s squared if it's the sample variance, and you have sigma squared if it is population variance. You square root those, get s and sigma if they are standard deviations. Eventually, we're going to get to P hat and P. P hat is your sample proportion, and P is the population proportion. And little r is your sample correlation, and rho, RHO, it kind of looks like an E in the bottom right here. That is your population correlation. The bottom two we'll get to a little later in the course, but for now you'll see these top three pretty often. All right, so I talked about how you compute the mean. To get the variance, it's going to be, it's still an expected value, but this is the sum of the squared distance that your data are from the mean, but each of those distances is multiplied by the corresponding probability of x. A more simpler formula is boxed out here. And so this is going to be the sum of x squared times p of x. So the square of your data multiplied by the corresponding probability of that x value, add those up and subtract the square of the mean. And that's going to give you your variance. So let's get applying some of these concepts. In problem 1 here, we want to know, what do you know if the sum of the probabilities in the probability model is less than 1? Well, if you don't have a value that is 1 and you have less than, it means you're missing something. You're missing a possibility. And so that's what you learn if the sum is not 1. Plus, it's not a valid probability model if the sum of all your probabilities is not 1. Problem 2. Blood types are recorded with an ABO type and an RH factor of a plus or minus. The following table is the probability model for the blood types in the US. And so you can see it's broken down 3 decimal places for the probabilities. You have all possible blood types, and if you add up all of those probabilities, which should come to 1, or really, really close to 1, depending on some rounding. We want to know, what is the rarest blood type in the US, and explain. So rarest means least likely or lowest probability. And as I look through this, I see a 0.015, 0.006, 0.006 for AB minus is the smallest value or your lowest probability. So it looks like AB minus because it has the smallest probability of 0.006 or 0.6%. Part B, how likely is a person in the US to have type O blood? And explain. So type O is either O positive or O negative. And so in this case, if you're type O, you could be either. And so you're going to add up those two probabilities, which is going to give you 0.44, it looks like. And there you have it. So you add up 0.374 and 0.066, and that gives you 0.4 nicely, or 44% of people in the US have type O blood. What proportion of people in the US have Rh positive blood? So now you're doing something similar, except you're adding all of the blood types with a positive sign. So A positive is 0.357, B positive is 0.085, 0.034 for the next, and 0.374 for the last. And when you add those up, you get what? So go ahead and calculate that. Let's see. You get about 85%. So most people have Rh positive type blood. It's good to be aware of. Generate a probability model for ABO type. So now you're ignoring plus minus. So we want a probability model, which means we need to list all the possibilities. When you're ignoring plus and minus, all we care about is A, B, AB, and O. So that's what I'm going to have in my table. Instead of all of those columns in the original table, I'm just going to have those 4, A, B, AB, and O. And what I need to know is, what are the probability of each. So for example, for A, I would need to add up a positive and a negative. And so that's going to be 0.42. When I add up 0.357, 0.063, I get 0.42 or 42%. And I do the same thing for the other groups. And this is what I've got. Just filling in my O there. And then you could check 0.42, 0.1, 0.04, and 0.4, add them all up, and you should get 0.5, 0.92, 0.96. And let me just make sure I didn't cancel anything out. So type O was 0.44. There we go. And now that adds to 1 or 100%. Part E, we're skipping. If you happen to be with a large group of at least 20, you could do this activity and see what the distribution looks like. But doing it virtually, that's pretty tough to do. So we're going to jump from problem 2. We've done 1, 2. Let's jump down to 4. Read this, see if how far you can get. Pause the video, and I am going to return in just a moment. Okay, so I know this was a little challenging because you haven't seen this one yet, but based on talking through the formulas earlier, let's see how far you're able to get. And in this case, this is a true story. My brothers are both in pharmaceutical sales. And here I've got a probability model for the number of doctors that they are able to convince to prescribe more of the company's drugs. And all the possibilities are none up through 6 doctors. Again, this is fictional data, but the idea holds. If you check that this is a probability model, a valid one, by adding up all the probabilities and that they sum to 1, that should work out fine. For part A, it's asking what is the expected value for the number of doctors that he will convince to prescribe more of his company's drugs to patients. So expected value, that is another way of asking what is the mean, or about how many doctors on average do we expect that will be convinced. So according to the formula, we are going to want to take each X, multiply by the corresponding P, so 0 times 0.095, 1 times 0.273, 2 times 0.329, and so forth. So each X times its probability, and you add up those products, and you'll get a value like 1.949. And it's fine that it's decimal, it's not a whole number. Obviously, they're not going to convince a part of a person, but this is on average. And so if you were to record many days or weeks of the number of doctors, that they or he successfully convinces, you might have 0, 0, 0, 1, 1, 2, 3, 6, 1, 1, 0, 0, 0, a whole bunch of values. If you average those, the average will be about 1.949. That's what this is saying. So on average, 1.949 doctors are convinced to prescribe more of the company's drugs. All right, so that's what we expect. How many doctors do you think you will convince in a standard 8-hour workday? So what I highlighted in the paragraph above is that this probability model is for a 3-hour period. So about 1.949 doctors within a 3-hour period. And there's almost 3-hour periods in 8. But essentially for every 3-hour period, there's 1.949. So there's a 3-hour period, another 3-hour period, and then a 2 out of 3-hour period. And so you've got 1.949 for the first 3-hour period, 1.949 for the second 3-hour period, and about 2/3 of that for the third period. And so we're going to have a value probably close to 5, but let's go ahead and see. Here we go. So 1.949 and 3 goes into 8. or 3-hour period into 8-hour period 2.67 times. That's where this value came from. And so when you multiply those two together, you get 5.197. All right, so here's another visual to show intuitively how you might get it, that from 1 to 4, which is 3-hour period, 1.949 doctors, another 1.949 for the second hour period, and then you've got part of that for the third, and you add up each of those sections and you'll get 5.197. And so there's the more mathematical side, and then there's a more intuitive one, and both are fine. All right, so what I'd like for you to do is pause the video at this point, and the two problems that we haven't done are 3 and 5. So give yourself some time, probably about 10 to 20 minutes to do them. And when you're ready, start the video back up to see the answers. Okay, so hopefully you gave a sincere effort at completing problems 3 and 5. Let's go through these pretty fast. So 3 is looking at commuting, different ways of commuting to work. And part A asks what value should be in the blank, or where I put a question mark. So the probability of taking some other means of travel. So to get this, you know that to be a probability model, the sum of the probabilities must be 1. When you add those up, you get 0.99, and so it's 0.01 off from 1. So the probability of other is 1% or 0.01. B, what is the probability that a randomly selected worker does not use public transportation to get to work? So there's a few ways you could do this. Not use public transportation, you could add up 0.76, 0.12, 0.03, 0.03, and 0.01. Or you could add up public transportation of 0.05 and realize that everything else but that 5% is not public transportation. So 1 minus 0.05 gets you to 0.95, and that's called the complement rule, because 1 minus public transportation will give you not public transportation. Part C, how likely is it that a randomly selected worker drives to work either alone or with others? So now, drives to work either alone or with others. So that would be the drive alone group, the carpool group, or you could even do the public transportation group in there. A lot of times students feel that taking the bus, is driving with others. But walking and work at home and other are likely not in that type of transportation. And so 0.76, 0.12, 0.05, you add those up and you get 0.93 or 93%. If you were to survey 1,000 adults, approximately how many would you expect to walk to work? Well, the probability of walking to work is 3% or 0.03. And so if you know 3% of people should walk to work and you have 1,000 of them, then 1,000 times 0.03 gives you 30, and that's how many you would expect to walk to work. So hopefully you did all right on problem 3. Let's take a look at number 5 here. The challenge with number 5 initially is just putting together your probability model. So that's the first thing to do. A local club plans to invest $10,000 to host a baseball game. They expect to sell tickets worth $15,000, but if it rains on the day of game, they're not going to sell any, and the club's going to lose all the money they invested. If the weather forecast for the day of game is 20% possibility of rain, is this a good investment? All right, so there's two possibilities. Either it rains or it doesn't rain. Now, if it rains, it says they won't sell any tickets, so they're going to be at a loss of 10,000. So that's a minus 10,000. But if it does rain, they'll sell $15,000 of tickets. But the profit, it has to take into account that they put in $10,000. And so they'll be up 5,000. You're also told that there's a 20% chance of rain. That's 0.2, which means there is a 80% or 0.8 chance of no rain, nice weather. So now that we have the probability model, we need to know, well, what is the expected profit? Because that's how I would decide whether it's a good investment, is to have an idea of, well, how much money do I expect to make? And based on this probability model, remember, expected value is x times p of x. So you have negative 10,000 times 0.2, 5,000 times 0.8, multiply them, add them up, and you'll get positive $2,000. So it's saying on average, we expect to gain $2,000. This is on a long-term investment. So if they were to do this, let's say for 20 different days, then on average, they will be up $2,000. So yes, you might view it as a good investment from that perspective. And that would be fine. But let me talk a little bit about variance, because we talked about that, but we haven't done it. If I want to know the variance of the game, so the variability in profit, that is going to be from this top formula here. So it's the same formula I had earlier. And you need the sum of the squared data times p of x minus mu squared. Well, we just got mu to be 2,000, so that's where this 2,000 squared came from. But to get the first term that I boxed out here, that's going to be negative 10,000 squared times 0.2 plus 5,000 squared times 0.8. And remember, when you square, you should not have any negative signs. So that negative 10,000 should become a positive value. If your calculator is not doing that, make sure you learn to use parentheses, or don't put the negative sign in, because you should know that it's going to be positive. But that's where the 40 million came from that calculation. The variance is 36 million, which is a big number, but when you root that, you've got the standard deviation to be 6,000. So how can we make use of this idea, the standard deviation? Well, there's something called the empirical rule, or it's also known as the 68, 95, 99.7% rule. And what it says is pretty simple, that about 68% of the data or possibilities should be within one standard deviation of the mean, so mu plus or minus 1 sigma. About 95% should be within 2 standard deviations, and 99.7% within 3. And so that's where these 3 come from. And now we want to know, well, what is the interval that provides how much profit we can expect? And let's go with 95% confidence. So 95% is mu plus or minus 2 sigma. Well, mu is 2,000, plus or minus 2 is part of the empirical rule. And 6,000 was our standard deviation. So when you calculate this, you've got that mu, the average profit, is somewhere between negative 10,000 and positive 14,000. So this might make you feel a little differently. Some of you may feel, oh, well, we could make a profit of up to $14,000. That's great. I'd go for it. And others may feel, well, $10,000 loss, that's too big of a gamble. I wouldn't want to risk that. Others of you may think, well, there's more positive region in this interval than negative, and so that seems more likely than not to be what happens, and so I'd take that risk. And all of these are valid approaches, valid mentalities. It's really up to you to get the information and then argue or justify your stance. And so there is some subjectivity here in terms of interpretation, not in terms of the statistics. And that's how you can make use of the empirical rule. Take care.